You might have wondered why some reactions happen when you put them together and why some reactions don't happen when you put things together. Like, why are we making such a big deal about galvanic and voltaic, the reactions that do occur, versus electrolysis, which is when we'll need to add electricity to make reactions happen? And that's a really good question. So in order to understand that and see what's happening here, we're going to talk about something called a cell potential. Now, it's important to remember in a practical example like water in a waterfall, all right? And water flows naturally down a waterfall. So in the picture there on the left, that's a really cool waterfall. I have no idea which one it is, but the water flows from the top to the bottom, and that's what happens normally. Now, if we really, really wanted water to go from the bottom to the top, we could hook up some kind of pulley system or a water wheel or something like that, and we could get the water from the bottom to the top, but it would take some work, okay? And this idea of having water flow one way and getting the water from the bottom to the top wouldn't be impossible but difficult if we put some work into it, applies really well to what we're going to talk about. So if water only flows spontaneously, i.e. by itself in one direction, electrons always flow in one direction spontaneously, and the other one it doesn't, all right? So it would be nice to know how to predict when electrons flow spontaneously, naturally, and when they don't. Now in chemistry, it's usually about going from a higher to a lower potential energy, but we're going to see an even better system to predict how this all works out. So in chemistry, and electrochemistry specifically, spontaneity can be measured through what's called electromotive force, EMF. And this is another term for what's called a cell potential value, E cell. Now, E cell value, cell potential, and electromotive force, same thing, all right? And these values will be measured in volts. Volts is a common system that's used, for example, in batteries. You can buy one of those kind of rectangular 9-volt batteries. The AA's and AAA's have their own voltage reading, et cetera, et cetera. Well, these are true volts as well, but these are volts applied for chemical systems. So let's see how this all works out. In your problem set for this chapter or online, you can find what's called a table of standard reduction potentials. And yes, you can use Google to have similar kind of versions, but please use my version in this section, all right? Because we're going to all be using the same list, and if we all use the same values, we should all get the same results. If you start going to Google or other textbooks, you might see different values, so just FYI. So in the version we're using, this is the table we're going to see. And there's some really cool kind of things that happen. So first of all, on the far right side are the E cell values, the volts that are going to happen. And you can see that like fluorine and 2 electrons going to 2 fluorides has a voltage of 2.87. That would be the cell potential of that reaction. So notice that it's listed as a reduction. Fluorine is gaining electrons to become fluoride. That's why they call these reduction half reactions. First of all, you're showing the electrons, so it's a half reaction, and electrons are reactants in all of those examples. So they're all reductions. So a good table, in my opinion, will be listed as reductions, which this is, and it'll be listed from most positive E cell value down to the smallest E cell value. And you can see they go from just under 3 volts there for fluorine down to just a little bit more than negative 3 volts on the bottom. We'll talk about that here in a little bit. Now these are the cell potentials measured under standard conditions, and that usually means 25 degrees Celsius, 1 mole per liter for the solutions, and 1 atmosphere. There's a lot of things you can get from it. First of all of these values are recorded here relative to what's called the She electrode. And in kind of a light blue color right there, that's the She electrode. It's H plus and 2 electrons going to H2 gas, and the cell potential is defined as 0 volts. So you can think of the She electrode as like the meter stick. We use a meter stick to measure meters length. We need something to measure cell potentials, and the She electrode is what it's going to be. Positive E cell values imply spontaneity, all right? So of these reductions, all right, the ones at the top with positive E cell values, those are the ones that are going to happen right now all by themselves. And there's some good culprits in here. So like fluorine going to fluoride, we've seen that fluoride just loves to form, all right? All the anions love to form. Fluorine going to fluoride has a huge E cell potential. 2.87 volts is pretty big. That means that reaction is going to happen. And if you look a little further down there, there's chlorine and there's all different kind of ones down there. So those are the reactions which happen right now. But there's also a lot of reactions with negative cell potentials, and those will be important to us here coming up. But just because it has a negative cell potential doesn't mean it doesn't have use, and we'll talk about that in a little bit. But what is kind of cool is that if you want to know the species which are more likely to be reduced, they're going to be in the upper left-hand corner. So fluorine loves to gain 2 electrons. H2O2 right under it loves to gain 2 electrons in some acid, etc., etc. All right. On the other hand, the things that like to be oxidized, we're going to see are in the lower right-hand corner. And we'll talk about that here in a little bit. You never have to memorize cell potential values. Just know that they're out there, and we'll see what we can do with them here in a little bit. All of those cell potentials on the last page can be reversed. You can take the reactants and make them products, turn the products into reactants, and you have a reverse cell potential. If you reverse a reaction, you change the sign of the cell potential, but not the magnitude of the E naught values. So as an example of this, let's say that we have zinc going to zinc 2 plus 2 electrons. This is an oxidation, by the way. But anyway, let's say the cell potential is positive 0.76 volts, and we were curious what the cell potential would be if we reverse it. No problem. Take the reactants, make them products, turn the products into reactants, and flip the sign of E. So if you flip that reaction, it would be zinc 2 plus 2 electrons making zinc metal, and the E naught value would be minus 0.76 volts. Now remember that positive E cell values are spontaneous. So what this tells the chemist is that zinc is much more likely to give up 2 electrons to become positive 2 than zinc 2 plus is to gain 2 electrons to become zinc metal. Positive E's, like the first one, those are the spontaneous ones. Those are going to happen. We're going to have to do some magic in order to make a negative E cell become positive. It can be done, but it takes some work. We'll talk about that more in a little bit. But the important part here, you wish to flip it, no problem. Flip reactants and products, change the sign of E, but don't change the magnitude of E. Now, because those E cell values are listed as reductions, you're going to see a lot of negative E values. Negative E values means that those aren't likely to be reduced, but they can be oxidized, all right? So the zinc metal going to zinc 2 plus is more likely than zinc 2 plus going to zinc because of those values. So when you see a negative E value, that just means it's more likely to occur in the opposite direction, i.e. as an oxidation, not a reduction. On the other hand, if you already have a positive E values, they're going to be great at reducing, but not so great at oxidizing. And we'll see examples of that here in a little bit. And remember, the agent thing is the opposite, which is just crazy. So a positive E cell value means you're going to have something that likes to be in that table anyway. It's going to be something that likes to be reduced, or it's a great oxidizing agent. That being said, in the example I used right here, this zinc metal likes to lose 2 electrons. It likes to be oxidized. It's going to be a great reducing agent. So be careful. This stuff can get a little weird, and reach out to me if you have any questions on it.